My name is Zhang. I am a research associate at the University of Southern California. I'm going to discuss a longitudinal study of functional brain complexity in progressive Alzheimer's diseases. I have no financial interest to disclose. Alzheimer's disease is a progressive, irreversible neurological disorder. Resting state FMR, measuring blood oxygenation level dependent signals, provides information on altered brain networks and function in this disease. Complexity analysis has been conducted in resting state fMRI data to investigate the functional brain abnormalities in Alzheimer's and mild cognitive impairment. Complexity can be computed through entropy. The concept of entropy in information theory was introduced by Shannon in 1948. It describes how much information, surprise, or uncertainty a system carries. In neuroscience, high complexity is an indication of healthy and robust systems with greater adaptive capacity. The degradation of this capacity is associated with loss of complexity in the dynamics of physiological systems. To compute entropy in time series, several variations of entropy were invented, including sample entropy and multiscale entropy. Sample entropy is the negative logarithm of the conditional probability that two sequences remain similar at the next time point, where self-matches are excluded in calculating the probability. In order to calculate multiscale entropy, coarse-grained time series are extracted from the original time series. Multiscale entropy stands for sample entropy across multiple scales. Here, lower scale number corresponds to higher frequency, and higher scale number corresponds to low frequency. It has been reported MSE at high and low frequencies may represent local and distributed information processing across brain regions. So far, resting state FMR complexity studies predominantly reviewed reduced complexity in mild cognitive impairment and Alzheimer's as compared to normal controls in cross-sectional cohorts. Here I display a few examples. However, the trajectory of resting state fMRI complexity in Alzheimer's progression remains unknown. In the present study, we conducted longitudinal resting state fMRI complexity analysis to investigate the Alzheimer's related functional brain changes over time. We leveraged the data from ADNI database. We were able to form 5 subject groups. Normal control group required every subject maintained healthy in every visit in ADNI. The NC to MCI group included subjects who converted from healthy to mild cognitive impairment. The MCI group required each subject maintained MCI once they were diagnosed as MCI. The MCI to AD group included subjects who converted from MCI to Alzheimer's. The AD group required each subject maintained Alzheimer's once they were diagnosed as Alzheimer's. Each subject in each group had at least 2 resting state fMRI scans from different visits, and the scans with frame-wise displacement larger than 0.2 mm were excluded. Each scan had repetition time 3 seconds and echo time 20 milliseconds. For the NC to MCI group, we required each subject had at least 1 scan while they were healthy and at least 1 scan while they were diagnosed as MCI. For the MCI to AD group, we required each subject had at least 1 scan while they were diagnosed as MCI and at least 1 scan while they were diagnosed as Alzheimer's. This table displays the demographic information for each group. The 5 groups matched in terms of education years, but not sex, age of the first resting state fMRI scan, and frame-wise displacement. Each scan went through the standard pre-processing procedure using contour box. Complexity analysis was performed using the in-house developed complexity toolbox with pattern length M equal to 2 and sensitivity threshold R equal to 0.3. Sample entropy for scales 1, 2, 3, and 4 were computed for each voxel. Then the area under the curve from scale 1 to scale 4, namely AUC multiscale entropy, was computed for each voxel. 14 meta-regions of interest were formed from Harvard-Oxford Atlas. Finally, sample entropy for each scale and AUC MSE were computed for each meta-ROI. We used linear mixed effects models to investigate the main effects of group and the time by group interactions. Model 1 evaluated complexity for the whole gray matter, and Model 2 to 6 were based on meta-ROI analyses. In all the models, normal control was used as a baseline group to be compared by other groups. Now, I'm going to show you the results. With respect to Model 1, we found a significant main effect of group. The normal control had greater global AUC MSE than all the other groups. We also found a significant group-by-time interaction. Global AUC MSE in the Alzheimer's group decayed faster than the normal control. Model 2 was based on the meta-ROI analysis. We found AUC MSE was greater in the normal control group than all the other groups in almost every meta-ROI, with only a few exceptions. We also found AUC MSE in the Alzheimer's group decayed faster than the normal control in the lateral temporal. Model 3 to 6 tested sample entropy from scale 1 to 4. We did not find significant main effects of group from Model 3 to 6. However, the results revealed significant group-by-time interactions. At scale 1, the NC to MCI group decayed faster than the normal control in the prefrontal and the lateral occipital. At scale 2, the Alzheimer's group decayed faster than the normal control in the lateral temporal. At scale 3, the Alzheimer's group decayed faster than the normal control in the prefrontal, middle frontal, inferior frontal, temporal pole, lateral temporal, and medial temporal. At scale 4, the Alzheimer's group decayed faster than the normal control in the lateral temporal and medial temporal. In summary, we found healthy elders had greater global gray matter AUC MSE than all the other groups, which was consistent with results reported in literature. The longitudinal changes of complexity could be reflected by sample entropy, local functional brain activities, decayed in the prefrontal and the lateral occipital in the early stage of disease, and the long-range communications were impacted in the frontal and the temporal regions in the later stage of the disease. In the end, we thank for the support from NIA and EDNI.